Welcome to Palsa Lab, your destination for amazing discoveries in science, space, AI, and technology. Today, we are embarking on a fascinating journey to the very beginning. How did life start? It's a journey that starts right now. Let's dive in.
The paradox of space right now. You are moving at 67,000 miles per hour. You don't feel it, but Earth is screaming through space, locked into a flat, circular groove around the Sun. Think of our solar system like a giant vinyl record. The planets, the asteroids, the moons, everything sits on that flat disk. We've sent rovers to Mars, crashed probes into Saturn, and even sent Voyager beyond the edge of the map. But almost everything we've ever done has happened on that flat record. What if you wanted to go up? What if you wanted to leave the disk entirely and look down at the Sun from the top? It sounds simple. Just point the rocket up, right? Wrong. In physics, up is the hardest place to go. In fact, it's 10 times harder to go a few million miles up than it is to travel billions of miles to the edge of the solar system. Today, we're looking at the impossible climb, the secrets hidden at the Sun's poles, and the cheat code for physics that might finally get us there. The enemy. Sideways speed. To understand why we're stuck on this flat plane, we have to talk about Earth's sideways speed. Because Earth is orbiting the Sun, it has a massive amount of momentum. When we launch a rocket, we inherit that speed. It's like jumping off a merry-go-round that's spinning at 30 kilometers per second. You don't start from zero. You start with a massive shove sideways. For missions to Mars or Jupiter, this shove is our best friend. We just add a little more speed, and we slide along the plane to the next planet. But if you want to go vertical, that sideways speed becomes your worst enemy. To go straight up, out of the planetary plane, you first have to cancel out every bit of that 30 kilometers per second sideways motion, just to stop drifting sideways. Only then can you start your climb. In rocket science terms, we call this delta 5, the change in velocity needed. Getting to Mars takes about 4 units of delta 5. Going straight up? It takes 30. It's the ultimate energy barrier. But why would we spend so much fuel just to get a different view? The mystery. What's hiding at the poles? Here's the thing. We are basically living in a house where we've never seen the roof. The Sun isn't just a glowing ball, it's a chaotic, magnetic engine. And the control room for that engine is at the poles. The fastest solar winds in the universe, streams of particles moving at nearly 2 million miles per hour, don't come from the Sun's equator. They blast out from the top and bottom. Every 11 years, the Sun's magnetic field does something crazy. It flips. North becomes south, and south becomes north. This solar cycle drives the space weather that can knock out our satellites and flip our power grids here on Earth. Scientists believe the seeds of this flip are planted at the poles, but because we're stuck on the flat record of the planets, we've only ever seen the poles from a tilted, blurry distance. We've had 2 pioneers try to get a better look. First, there was Ulysses in 1990. It couldn't carry enough fuel to go up, so it took a detour to Jupiter, using the giant planet's gravity like a slingshot to fling itself out of the plane. It worked, but Ulysses didn't have cameras. It could feel the wind, but it couldn't see the face of the Sun. Then came Solar Orbiter in 2020. Using a series of gravity assists from Venus, it's slowly, very slowly, tilting its orbit. In March 2025, it gave us our first ever real glimpse of the South Pole. What it saw was a tangled, chaotic magnetic mess. It was nothing like the organized loops we see from Earth. It was a revelation. But to see the whole picture, to see our solar system's true shape, we need to go even higher. The shape. The deflated croissant. There's another mystery waiting for us, up there. It's the shape of our home, the heliosphere. The heliosphere is the giant magnetic bubble the sun blows around itself, protecting us from the radiation of the rest of the galaxy. For 50 years, we pictured it like a comet, a round head with a long, streaming tail behind it as we move through the galaxy. But recently, new computer models suggested something that sounds ridiculous. They suggest our solar bubble isn't a comet, it's a deflated croissant. A rounded center with two short, stubby jets and almost no tail. We can't be sure because every spacecraft we've sent out, even the legendary Voyager 1 and 2, stayed relatively flat. They left the bubble through the sides. To know for sure if we live in a comet or a croissant, we need a bird's eye view. We need to look down from the top. The cheat code. The Solar Oberth maneuver. So, if building a bigger rocket won't work, how do we get there? This is where space navigation gets weird. If you want to go up and away from the sun, the best way to do it is to first fall toward it. This is called the Solar Oberth maneuver. Named after Hermann Oberth, one of the fathers of rocketry, it relies on a strange rule of physics. Rockets are more efficient when they are moving fast. Instead of burning your fuel out in deep space where you're moving slowly, you drop your spacecraft inward, diving toward the sun. Gravity pulls you in, faster and faster, until you're screaming past the sun at hundreds of kilometers per second. At that exact moment, at your fastest and closest point, you fire your engines. Because you're already moving so fast, that extra kick from the engine adds a massive amount of orbital energy, way more than it would have anywhere else. The sun's gravity doesn't just pull you, it acts as a launch pad. This maneuver could give a probe enough oomph to cancel out that sideways Earth speed and climb straight out of the plane. But it's risky. You're flying into a furnace, traveling at speeds that would melt most metals, and you have to fire your engine with perfect precision. It's the ultimate high-stakes dive. The alternative. Sailing on light. If a high-speed dive sounds too scary, there is another way: solar sails. Imagine a sheet of reflective material, thinner than a human hair, but the size of a football field. It doesn't use fuel. Instead, it catches the tiny push of sunlight. Over years, that constant, gentle pressure can slowly tilt a spacecraft's orbit, spiraling it up and out of the planetary plane. It's slow, it's steady, and it's elegant. Some scientists even propose a hybrid mission. Use a solar sail to spiral in close to the sun, then perform a high-speed Oberth burn to go vertical. It's the best of both worlds. Conclusion. The new perspective. If we pull this off, the rewards will be breathtaking. Beyond the dust of the planetary plane, the view gets cleaner. We'd see the planets as a perfect, flat ring. We'd see the sun's poles in high definition, finally understanding the engine that drives our space weather. And we'd see the true shape of our heliosphere, our home bubble, for the first time. It reminds us that in space, the most direct path is rarely a straight line. Sometimes, to go up, you have to fall. To go fast, you have to get close to the fire. So, what do you think? If you were mission control, would you bet on the slow, steady solar sail, or the high-speed Oberth dive? Let me know in the comments. And if you want to keep exploring the weirdest corners of our universe, hit that subscribe button. I'll see you in the next one.